Hello, so in this video we're going to be talking about Taylor polynomials for just a little bit and then a very special type of Taylor series called the Maclaurin series. So first of all, remember that the Taylor series is a power function, so every single term in the series will be raised to some power of n. So each term in the series can really be thought of as kind of like a polynomial because a polynomial represents adding a lot of things raised to some highest power. In this case, that will be whatever the series goes to. So if we have a zeroth order Taylor polynomial, that's just going to be the first term. This is the first term that we get in the Taylor series. Again, plug in n equals 0 into this series right here. F0 of c means the zeroth derivative, so that means f of c. 0 factorial is 1, and if n right here is equal to 0, if that n is equal to 0, then x minus c to the 0 is 1. So that's why we just get f of c here. In a first order Taylor polynomial, we go to the first two terms of the series. Now, this is, again, the n equals 0 term. This is the n equals 1 term, because if we plug in 1, we get first derivative of f at c. That's this right here. We get 1 factorial, which is 1, and then x minus c raised to the 1. So it looks like that. So hopefully you can deduce that if we had a second order polynomial, it would look something like this. We just go out to that term. And the way I like to remember them is whatever the order of the polynomial is, that's the biggest power that you go out to. So Taylor polynomials are useful because if we take them out to an nth order, the larger the number of capital N is in this case, or the power that we take the Taylor series out to, the more accurate it's going to be in an approximation for our function. So if we look at that with the last one we had, remember this counter capital N right here, this is going to generate a function. T of x is a function. So if I plug in different values of n, it'll give me different functions. Well, these functions are actually the Taylor polynomials. At capital N is 0, this only contains a 0th term in the series. So this is the 0th order and really, we don't really talk about 0th order Taylor polynomials, but I just like to say that so you can see how the numbers work out. If we go to n equals 1, so we include that first linear term, again, it becomes a linear function. If we include the term with a quadratic, it becomes quadratic, like that. And if n equals 3, we're including the cubic term, so it's going to be a cubic function, and so on and so forth. So as you can see, we've just cycled through 4 different polynomials from capital N is 0 to capital N equals 3. And each of those polynomials just represents the graph of a line. And if we go all the way out to a very high polynomial, we end up getting better and better and better approximations for the function. So Taylor polynomials come up especially in multiple choice questions on the AP exam. So it's just good to know what they are, but basically this is all there is to it. And within this, pretend you're given a Taylor polynomial. Well, you can also, if you're given that polynomial, usually you'll be able to do things like find what the second derivative of a function is or something like that. They love to ask questions like that too. So just be prepared for that. So the next quick thing I want to talk about are Maclaurin series. And you look at, it's class all over the place right here. We're going to the nines on this video. All right, anyway, so if we have a Taylor series centered at c equals 0, this is actually called a Maclaurin series, okay? So these series are actually really good to work with because a lot of times when you plug in x equals 0 to a derivative or any function, you usually get something fairly simple coming out, though that's not always a guarantee. So a lot of times Maclaurin series are easier to work with than Taylor series. So let's look at an example. If I want to look at the Maclaurin series for e to the x, well, that's really easy because the whatever derivative of e to the x is just going to be e to the x, so they never change. So this value up here is always going to be the nth derivative evaluated at x equals 0, which will just be e to the 0. The factorial stays, the x to the n stays, and there we go. We got this really nifty series for e to the x, and this is, in fact, the series representation of e to the x. Now, what's really cool about this one is that if we do an interval of convergence, if we do the ratio test on it, we end up getting this limit right here, which as n goes to infinity, this goes to 0. So it satisfies the ratio test everywhere of being always less than 1. So the Maclaurin series for e to the x converges everywhere. And so this is what that looks like. If we come here and plot e to the x, and then plot the series for e to the x. And we do that, what we see, let's get rid of these lines right here. What we see is that if I take n down, again, at the 0th order polynomial, if you want to call it that, or the constant, that's not a very good approximation. Linear gets a little bit better, quadratic a little bit better, cubic a little bit better, 4th order, 5th order, 7th order, keep on going. And in this one, you might say, hey, that looks like it's going toward an interval of convergence, but if I keep making this number go higher and higher, it just keeps extending out. And it turns out I could make the slider go for a really long time. And actually Desmos would kind of crash. Let's see if we can make that happen. It usually happens with 100 terms. So he's trying to, there you go. So that's like Desmos just freaked out right here. And something within the code itself. This is a classic case of noise, actually diverging noise. So in this case, when they're graphing this function, eventually we're getting to an issue with computer noise that's driving our solution to go bad. And this is actually a really good example. Series are approximations, so they're not exact solutions. So we're actually at the mercy of the computers that we use to solve some of these series problems. And all computers, they have a breaking point that you can take them to for numerical solutions. But as you can see, I mean, that this is just with Desmos, but if we use this equation anywhere really within the proximity, especially if x equals 0, but in many x values, this would work. Now, if we didn't want to deal with all of this stuff out here, all of this nasty noise, we could just make this a Taylor series centered at x equals negative 35 and shift everything over so we wouldn't get that noise. You can always make a Taylor series, but like I said, just kind of a good lesson to learn about computers and numerical methods and approximations and all that. But anyway, so that's both of these, and then we'll have maybe 1 or 2 more videos coming up in the next couple days that'll describe error approximations in these and how we can take derivatives and integrals of Taylor series and Maclaurin series, which is oh so fun. So anyway, I will see you then.